One of the brightest stars in your night sky just did something no star has ever been caught doing before. In 2019, Betelgeuse ripped off a chunk of its own surface and hurled it into space. The blast was 400 billion times more powerful than anything our sun has ever produced. It shattered a pulsation rhythm that had been beating steadily for nearly 2 centuries, and the star is still recovering. Then, in 2025, astronomers confirmed something hiding in the chaos, a secret companion star, buried so deep inside Betelgeuse's atmosphere that it took decades of suspicion and 8 years of Hubble observations to prove it was real. Scientists are not worried that Betelgeuse will explode tomorrow. They are worried because one of the most famous stars in the sky is behaving in ways no one fully understands. If you enjoy deep explorations of the universe and the science behind its strangest mysteries, it would mean a lot if you hit that like button and subscribe to the channel. Now, settle in and get yourself comfortable. Let's begin. Look up on any clear winter night and find the constellation Orion. It is one of the easiest patterns in the entire sky. 3 stars in a neat diagonal line form the belt. Below them hangs a faint smudge that marks the hunter's sword, and up at the top left corner, marking what ancient astronomers called the shoulder, burns a star that looks nothing like its neighbours. It glows deep orange-red, a colour so distinct that even casual observers notice it without being told what to look for. That star is Betelgeuse. And right now, it is one of the most intensely studied objects in all of modern astronomy. Not because it is rare, not because it is far away, but because over the past several years this star has done things that no one fully anticipated, things that forced scientists to rethink assumptions they had held for decades. To understand why Betelgeuse has the astronomical community so focused, you first need to understand what kind of star it is and why that matters. Betelgeuse is a red supergiant. That classification alone places it among the most extreme objects in stellar physics. A red supergiant is a star nearing the end of its life, a massive sun that has exhausted the hydrogen fuel in its core and begun burning heavier elements in successive shells. As this process unfolds, the star swells to extraordinary dimensions. Its outer layers expand outward, cooling as they go, which is why the surface glows red rather than white or blue. The star becomes enormous but diffuse, a bloated giant radiating energy across a surface area that dwarfs anything in our solar system. In the case of Betelgeuse, the numbers are staggering. Its radius stretches somewhere between 640 and 764 times the radius of our Sun. If you removed the Sun from the centre of our solar system and dropped Betelgeuse in its place, the star's surface would swallow Mercury, Venus, Earth, and Mars entirely. It would push outward into the asteroid belt, consuming roughly 3.5 astronomical units of space in every direction. Everything inside that boundary would exist within the body of the star itself. Our entire inner solar system would be interior real estate. That is how large Betelgeuse is, and yet, for all that size, the star is not particularly dense. Red supergiants are essentially vast, tenuous atmospheres surrounding a comparatively small and intensely hot core. The outer layers are so diffuse that in some regions the boundary between star and surrounding space becomes genuinely ambiguous. There is no sharp edge. The atmosphere fades gradually into the circumstellar environment, a haze of gas and dust that extends even farther into space. To understand why a star this enormous is also a star that is dying, you need to understand what is happening deep inside it, far below the bloated red surface that we observe from Earth. Every star is a balancing act between 2 opposing forces. Gravity pulls inward, trying to crush all the stellar material down into the smallest possible volume. Nuclear fusion pushes outward, generating the energy and pressure that resists gravitational collapse. For most of a star's life, these forces hold each other in check. Our Sun has been maintaining this balance for roughly 4.5 billion years, fusing hydrogen into helium in its core at a steady, sustainable pace. It will continue doing so for another 5 billion years or so. The fuel supply is enormous and the burn rate is moderate. Massive stars like Betelgeuse play by different rules. A star born with 15 or 20 times the mass of the Sun burns through its hydrogen fuel not in billions of years but in millions. The greater gravitational pressure in the core demands higher temperatures and more intense fusion to maintain equilibrium. The star burns hotter, brighter, and faster. By the time a star like Betelgeuse exhausts the hydrogen in its core, it has lived only about 10 million years, a blink compared to our Sun's lifespan. But running out of hydrogen is not the end. It is the beginning of the end, a slow cascade of increasingly desperate nuclear reactions that will ultimately seal the star's fate. When the hydrogen in the core is gone, the core contracts under gravity, heating up until it reaches temperatures high enough to ignite helium fusion. Helium atoms begin fusing into carbon and oxygen. This new energy source stabilizes the core temporarily, but helium burns faster than hydrogen did. The fuel runs out sooner. When the helium is exhausted, the core contracts again, heats up again, and begins fusing carbon into neon, magnesium, and sodium. Then neon fuses into oxygen and magnesium. Then oxygen fuses into silicon and sulfur. Each successive fuel source burns at higher temperatures and is consumed more quickly than the one before it. The result is a star with an internal structure that resembles an onion. Layers of different elements are nested inside one another, each one representing a different stage of nuclear burning. The outermost envelope is still mostly hydrogen and helium. Beneath that sits a shell where hydrogen is actively fusing. Below that, a helium-burning shell, then carbon, then neon, then oxygen, and at the very center, the innermost core, where the most advanced fusion reactions are taking place. Each layer is hotter, denser, and more compressed than the one above it. The deeper you go, the more extreme the conditions become. This layered structure is beautiful in its physics and terrifying in its implications, because there is a final stage in this sequence that the star cannot survive. When silicon fusion begins in the innermost core, it produces iron, and iron is the end of the line. Every fusion reaction up to iron releases energy, which is what keeps the star alive. But fusing iron does not release energy. It absorbs it. Iron is the ash of stellar nucleosynthesis, the final waste product that cannot be burned further for fuel. Once the core fills with iron, no amount of gravitational contraction can ignite a new energy source. The star has written a check that physics cannot cash. The core collapses in a fraction of a second, triggering a supernova explosion that blasts the outer layers into space at tens of thousands of kilometers per second. We do not know exactly which burning stage Betelgeuse currently occupies. The star is almost certainly past helium burning and likely engaged in carbon fusion or beyond. But pinning down the precise stage requires knowing the star's mass, distance, and internal structure with a precision that current observations cannot provide. What we do know is that the clock is running. Each successive burning stage is shorter than the last. Hydrogen burning lasted millions of years. Helium burning lasted hundreds of thousands. Carbon burning lasts perhaps 1,000 years. Neon burning lasts roughly a year. Oxygen burning lasts months. And silicon burning, the final stage, lasts approximately 1 day. One single day of silicon fusion, and then the iron core forms, and the star dies. The acceleration is relentless. From the outside, nothing visible changes during these final stages. The surface of the red supergiant looks the same whether the core is burning carbon or oxygen. The death is invisible until the very end. Betelgeuse sits roughly 650 light-years from Earth, although that number carries more uncertainty than you might expect for such a bright, well-known star. Different measurement techniques have produced estimates ranging from around 400 to over 600 light-years. The European Space Agency's Gaia mission, which has revolutionized stellar distance measurements for billions of fainter stars, cannot produce reliable results for Betelgeuse because the star is simply too bright. it saturates the instruments. So one of the most famous stars in the sky still has a distance that astronomers cannot pin down with full confidence. That uncertainty ripples outward into everything else. Distance affects calculations of luminosity, radius, mass, and evolutionary stage. Change the distance, and you change the model. This is one of the first hints that Betelgeuse, despite centuries of observation, remains a more elusive target than its brilliance might suggest. What astronomers do know with confidence is that Betelgeuse is massive. Estimates of its mass range from slightly under 10 to a little over 20 times the mass of our Sun. That spread is wide, and it matters enormously because a star's mass determines its fate. Stars above roughly 8 solar masses are destined to end their lives in a core collapse supernova, one of the most violent events the universe can produce. Betelgeuse sits comfortably above that threshold. Its death, whenever it comes, will be explosive. The core will collapse in a fraction of a second. The outer layers will be blasted into space at tens of thousands of kilometers per second, and for a few weeks the explosion will shine with the luminosity of billions of suns. That future is not in question. The only question is when. But before we get to the supernova question, there is something else about Betelgeuse that made it uniquely valuable to astronomers long before the recent drama. The star pulsates. Like a slow cosmic heartbeat, Betelgeuse expands and contracts in a rhythm that changes its brightness over time. This pulsation has been documented for nearly 200 years. Observers stretching back to the 1800s recorded systematic variations in the star's magnitude, and by the 20th century, astronomers had established a primary pulsation period of approximately 400 days. Every 400 days or so, Betelgeuse would brighten, then dim, then brighten again. The cycle was not perfectly regular, which is why the star is classified as a semi-regular variable rather than a strictly periodic one. But the pattern was consistent enough that it became one of the defining characteristics of the star. Astronomers used it to study internal structure, to model how energy moves through the convective envelope of a supergiant, and to test theories about how massive stars behave in their final evolutionary stages. There was also a secondary cycle, a longer oscillation with a period of roughly 2,100 days, about 5 3/4 years. This cycle modulated the star's brightness on top of the primary pulsation, creating a complex pattern that researchers tracked for decades. The origin of this secondary period was unclear. Some scientists attributed it to giant convection cells churning across the star's surface. Others proposed different pulsation modes interacting with one another. The secondary cycle remained a puzzle, but not an urgent one. Betelgeuse was behaving more or less as expected for a red supergiant. The star was interesting, well-studied, and scientifically productive. But it was not alarming. Then came the winter of 2019. In late October of that year, observers noticed that Betelgeuse was getting dimmer. This was not unusual in itself. The star dims and brightens regularly, but by December, the dimming had accelerated. Betelgeuse was fading faster and deeper than anyone had seen in the modern era of observation. By January 2020, the star had dropped to roughly 65% of its normal brightness. It continued falling. On February 9th, 2020, Betelgeuse reached a visual magnitude of approximately positive 1.64, the faintest it had been in nearly 2 centuries of recorded observation. A star that normally ranks among the 10 brightest in the night sky had slipped below the top 20. You could see the difference with your naked eyes. Orion looked lopsided, its bright shoulder suddenly dimmed to a shadow of its former self. The event became known as the Great Dimming, and it ignited a firestorm of public and scientific attention. Social media exploded with speculation. News headlines screamed that Betelgeuse might be about to explode. The word supernova trended worldwide. Amateur astronomers aimed their telescopes at Orion with a mixture of excitement and dread. Professional observatories redirected resources to monitor the star around the clock. Everyone wanted to know the same thing. Was this it? Was Betelgeuse dying right in front of us? The supernova hypothesis was never the most likely explanation, and most professional astronomers said so at the time. But the public fascination was understandable. Betelgeuse is the nearest red supergiant to Earth. It will go supernova eventually. And its brightness had just plummeted in a way that had no precedent in the historical record. The combination of proximity, inevitability, and unprecedented behavior created a perfect storm of attention. For a few months, Betelgeuse was the most watched star in the world. By March 2020, the star began to recover. Its brightness climbed back toward normal values, and by April it had returned to roughly its pre-dimming luminosity. The immediate crisis was over, but the scientific investigation was just beginning. What had caused such an extreme and rapid drop in brightness? The answer, when it finally came together, was stranger and more dramatic than most people expected. The forensic trail began not with the dimming itself, but with observations taken months earlier. Andrea Dupree and her team at the Center for Astrophysics at Harvard and Smithsonian had been monitoring Betelgeuse with the Hubble Space Telescope's ultraviolet capabilities long before the visible dimming attracted public attention. In the months leading up to the Great Dimming, Hubble detected something unusual. Ultraviolet spectral signatures revealed hot, dense material moving rapidly outward through Betelgeuse's atmosphere. Something energetic had happened deep inside the star and was now propagating through its outer layers at significant velocity. At the time, the significance of this observation was not fully appreciated. It was only later, when astronomers pieced together the full timeline, that the Hubble ultraviolet data emerged as the earliest forensic evidence of what was about to unfold. The hot material Hubble detected was the leading edge of a shockwave, the first visible sign of a convective eruption that had originated deep within the star's interior. That shockwave would take months to fully develop, to reach the photosphere, and to blast material into space. But Hubble caught the early tremors. Astronomers analysing data from Hubble, the European Southern Observatory's very large telescope, and several other facilities pieced together a scenario that reads more like a disaster movie than a routine stellar observation. In early 2019, months before the visible dimming began, a massive convective plume had bubbled up from deep within Betelgeuse's interior. Convection is the process by which hot material rises and cooler material sinks, the same mechanism that drives weather patterns on Earth and boiling motion in a pot of water. Inside a red supergiant, convective cells operate on a mind-bending scale. This particular plume stretched more than 1 million miles across. It surged upward through the star's outer layers, generating shocks and pulsations as it went. Those shocks did something that had never been directly observed on any normal star before. They blasted a chunk of Betelgeuse's photosphere, the visible surface layer, clean off the star and into space. Astronomers called it a surface mass ejection, and the term barely captures the violence of the event. The ejected material weighed roughly several times the mass of our moon. It was launched outward at significant velocity, tearing away from the star's gravitational grip and expanding into the surrounding space. As this material moved away from Betelgeuse and cooled, it condensed into an enormous cloud of dust particles. That dust cloud, now drifting between Betelgeuse and Earth, blocked a substantial fraction of the star's light from reaching our telescopes. The Great Dimming was not a signal from the star's core. It was not a prelude to supernova. It was the shadow of a wound. Our sun produces something superficially similar, called a coronal mass ejection, where the solar corona throws off bursts of plasma and magnetic field into space. These events can disrupt satellite communications and create beautiful auroral displays on Earth. But the surface mass ejection from Betelgeuse was on an entirely different scale. It blasted off roughly 400 billion times as much mass as a typical solar coronal mass ejection. The comparison is almost absurd. It is like comparing a sneeze to a volcanic eruption. The two phenomena may share some surface-level resemblance, but they operate in fundamentally different regimes of energy and mass. The Very Large Telescope Sphere instrument captured direct images of Betelgeuse's surface during the dimming event, and they were haunting. The star's southern hemisphere had gone visibly dark. What had been a roughly uniform disk of glowing stellar surface now showed a dramatic asymmetry, with one entire quadrant substantially dimmer than the rest. Scientists were literally watching the aftermath of a stellar injury in real time, seeing the wound on the star's face where the photosphere had been torn away. But the great dimming itself, as dramatic as it was, turned out to be only the most visible symptom of something deeper. The surface mass ejection did not just create a temporary dust cloud, it fundamentally disrupted the internal mechanics of the star. Remember the 400-day pulsation cycle, that steady heartbeat that astronomers had measured for nearly 2 centuries? After the ejection event, it vanished. The pulsation simply stopped. For more than 2 years following the Great Dimming, Betelgeuse showed no evidence of its familiar 400-day rhythm in either its brightness variations or its radial velocity measurements. 2 centuries of reliable, documented pulsation gone. Andrea Dupree described the aftermath in vivid terms. The star's interior convection cells, the massive currents of rising and sinking material that normally drive the pulsation, appeared to be sloshing around chaotically. She compared it to the vibrations of an unbalanced washing machine tub. The outer layers of the atmosphere seemed to be recovering, but the surface itself was still bouncing and oscillating erratically. She used another analogy that captured the unsettled state perfectly. The photosphere was rebuilding itself, but it was jiggling like a plate of gelatin on a table, stable from a distance, wobbly up close. This disruption was unprecedented, not just for Betelgeuse, but for any star of this type. Astronomers had theoretical models for how red supergiants pulsate, how convective energy drives rhythmic expansion and contraction, and how those cycles relate to the star's internal structure. But none of those models had accounted for what happens when a star literally ejects a piece of its own surface into space. The event rewrote the textbook on red supergiant behavior in real time. Eventually, signs of recovery appeared. The pulsation began to rebuild, but initially at twice the frequency of the original cycle, a transient response that some researchers compared to plucking a string on an instrument and hearing an overtone before the fundamental note reasserts itself. The expectation was that over time, the familiar 400-day period would eventually return. But the recovery was slow, and the star's behavior remained unsettled and difficult to predict. What made this even more significant was the sheer amount of mass involved. The material ejected during the surface mass ejection represented a significant fraction of Betelgeuse's total annual mass loss rate. Red supergiants shed mass continuously through stellar winds, a slow but steady outflow of gas that carries material away from the star over millions of years. This mass loss matters because it determines how much material the star retains when it finally explodes. A star that loses more mass before the supernova produces a different kind of explosion and leaves behind a different kind of remnant, either a neutron star or a black hole, depending on how much core mass remains. The surface mass ejection demonstrated that episodic, violent mass loss events could contribute an amount comparable to the steady stellar wind in a single explosive episode. This was not just a curiosity about Betelgeuse. It was a revelation about how red supergiants in general might shed their mass in the final stages before supernova. If these events happen periodically, if convective plumes routinely build up enough energy to blast photospheric material into space, then the mass loss histories of red supergiants might be far more dynamic and irregular than previous models assumed. Scientists had never directly witnessed a surface mass ejection from a normal star before. Betelgeuse was the first, and the only reason they caught it was because Betelgeuse happens to be enormous and close enough that its surface can be directly resolved by modern instruments. If the same event had occurred on a more distant red supergiant, the dimming would have been noticed, but the surface detail, the asymmetric darkening, the spectroscopic signatures of outflowing material, all of that would have been invisible. Betelgeuse offered a front-row seat to a phenomenon that might be common across the universe, but had simply never been observed in this kind of detail. By 2022, when the full analysis of the surface mass ejection was published, the scientific picture was clearer but no less remarkable. Betelgeuse had experienced the most violent mass loss event ever directly documented on a normal star. The blast had disrupted internal dynamics that had been stable for at least 2 centuries. The star was slowly recovering, but its behavior remained unusual and difficult to model cleanly, and the implications extended far beyond one star in Orion. The event opened a new window into the late-stage evolution of massive stars, a phase that remains one of the least understood chapters in stellar physics. But here is what kept astronomers watching long after the Great Dimming faded from public attention. The surface mass ejection explained the dramatic dimming event. It explained the dust cloud, the asymmetric darkening, the disrupted pulsation. It was a satisfying answer to the most visible question, but it did not explain everything. There was still that mysterious secondary cycle, the 2,100-day brightness oscillation that had been documented for decades before the Great Dimming ever occurred. The surface mass ejection did not account for it. Internal pulsation models did not fully account for it either. Something else was going on with Betelgeuse, something the ejection event had overshadowed but not erased. And in the years that followed, as astronomers continued monitoring the star with Hubble, with ground-based spectroscopes, with every instrument they could bring to bear, they found evidence of something hiding in the data, something small, something that had been there all along, orbiting silently inside the chaos of the supergiant's atmosphere, a companion, and its discovery would change the story of Betelgeuse all over again. The Great Dimming grabbed headlines. The surface mass ejection rewrote textbooks, but even as Betelgeuse was recovering from its most dramatic episode in recorded history, a quieter mystery had been sitting in the data for decades, patiently waiting for someone to solve it. And when the answer finally arrived, it did not come in the form of an explosion or a dust cloud or a sudden darkening visible to the naked eye. It came in the form of a tiny, faint point of light that had been hiding in plain sight, buried inside the atmosphere of a star more than 1 billion miles wide. To understand why this discovery mattered so much, you need to go back to the brightness patterns that astronomers had been tracking long before the winter of 2019. Betelgeuse has 2 well-documented cycles of variability. The first is the roughly 400-day pulsation that drives the star's primary brightness changes. That cycle is understood reasonably well. It arises from the Kappa mechanism, a process in which layers of the star's atmosphere become opaque to radiation, trapping heat, expanding outward, then becoming transparent again, releasing the energy, and contracting. This rhythmic breathing is common among pulsating stars, and for Betelgeuse, it had been measured reliably since the 1800s. It is the star's heartbeat, slow and steady, roughly 1 full cycle per year and a month. But underneath that primary rhythm, there was always a second signal, a longer, subtler oscillation with a period of approximately 2,100 days, roughly 5 3/4 to 6 Earth years. This secondary cycle modulated Betelgeuse's overall brightness on top of the faster pulsation, creating a more complex light curve that required careful long-term monitoring to detect. Astronomers had documented this longer cycle for decades, but its origin remained stubbornly unclear. Several explanations were proposed over the years. One popular idea attributed the secondary period to giant convection cells on Betelgeuse's surface. Red supergiants do not have millions of small convective granules like the Sun. Instead, they have a small number of enormous convective plumes, each one spanning a significant fraction of the star's diameter. These giant cells could, in theory, produce brightness variations as they rise and fall on timescales of several years. The problem was that simulations of convective behavior did not cleanly reproduce the observed periodicity. Convection is inherently chaotic. It produces irregular fluctuations, not the relatively consistent cycle that the observations showed. Another explanation proposed that the secondary period was a different pulsation mode, perhaps a higher-order overtone interacting with the fundamental 400-day mode. This was mathematically plausible but difficult to confirm observationally. The interactions between multiple pulsation modes in a star as complex and poorly constrained as Betelgeuse are notoriously hard to model. Without a clear theoretical prediction that matched the data, this idea remained speculative. A third hypothesis, quieter and less prominent for years, proposed something entirely different. Maybe the secondary cycle was not intrinsic to Betelgeuse at all. Maybe it was caused by something external, specifically by a companion star orbiting the red supergiant, with a period that matched the observed brightness modulation. This idea had floated around the edges of Betelgeuse research for a long time, but it faced an obvious challenge. Nobody had ever seen a companion, and given how bright and enormous Betelgeuse is, detecting a small companion star orbiting close to it would be extraordinarily difficult. The glare from the supergiant would overwhelm any faint nearby source. It would be like trying to spot a firefly hovering next to a searchlight. Still, the companion hypothesis had certain advantages. It was clean. A small star orbiting Betelgeuse every 6 years would naturally produce periodic effects on the supergiant's atmosphere. As the companion moved through its orbit, it could stir up gas, modulate dust production, and create observable changes in brightness and spectral features. The period would be regular, tied to the orbital mechanics rather than to the messy physics of convection. And it would explain why the secondary cycle persisted so consistently over decades, while convective models struggled to produce that kind of regularity. The hypothesis gained serious momentum in 2024, when 2 independent research groups published studies that both pointed toward the same conclusion. One team analysed Betelgeuse's radial velocity measurements, the subtle Doppler shifts in the star's spectral lines caused by the gravitational tug of an orbiting body. Their calculations suggested that a companion with roughly 1.17 solar masses orbiting at a distance of about 8.5 astronomical units could account for the observed 2,100-day periodicity, the fluctuating radial velocity measurements, and even certain characteristics of Betelgeuse's relatively moderate radius and low variation in effective temperature. The second team took a different approach, examining brightness records spanning more than a century. They independently arrived at a similar conclusion, proposing a close-in stellar companion with an orbital period of approximately 5.78 years, possibly less massive and less luminous than our Sun. Neither study claimed a confirmed detection. The companion remained hypothetical, inferred from indirect evidence rather than directly observed. But the convergence of 2 independent analyses pointing toward the same answer was compelling. The astronomical community began treating the companion hypothesis as a serious leading candidate rather than a fringe idea. Then came May 2025. A team studying Betelgeuse in ultraviolet and X-ray wavelengths published results that narrowed the possibilities significantly. Their observations effectively ruled out the chance that the companion was a compact object, meaning it was not a white dwarf and not a neutron star. Those types of stellar remnants produce characteristic X-ray signatures that were simply not present in the data. Whatever was orbiting Betelgeuse, it appeared to be a normal, low-mass, relatively young star. The team estimated that the companion's mass was likely less than 1.5 solar masses, and possibly less than 1 solar mass. This was consistent with the earlier predictions, and further tightened the theoretical picture, but direct visual detection remained elusive. The companion was still, at that point, an invisible gravitational ghost inferred from its effects on the supergiant. The breakthrough arrived in July 2025, and it came from an instrument specifically designed to see things that are very close to very bright objects. A team led by Steve Howell at NASA's Ames Research Center used the Alupeke instrument on the Gemini North Telescope in Hawaii. Alupeke is a speckle imaging camera, a device that takes extremely rapid exposures and uses computational techniques to cut through the blurring caused by Earth's atmosphere. It is purpose-built for resolving fine details near bright stars, exactly the kind of observation needed to spot a faint companion hiding in Betelgeuse's glare. The team employed a clever observational strategy built on a specific prediction. If a companion existed with the orbital parameters proposed by the 2024 studies, then its position relative to Betelgeuse as seen from Earth would be predictable. At certain points in its orbit, the companion would be directly behind or in front of the supergiant from our line of sight, making it undetectable. At other points, it would swing out to its maximum angular separation, the moment when it would be easiest to spot against the overwhelming brightness of its giant host. Howell's team compared two sets of Alipeki observations. The first was taken in 2020, during the Great Dimming event. At that time, the companion was predicted to be almost directly aligned with Betelgeuse along our line of sight. If the companion existed, it should have been invisible in those images. And it was. No companion appeared. The second set of observations was taken in December 2024, just 3 days after the predicted moment of greatest elongation, the point in the orbit when the companion would be at its widest apparent separation from the supergiant. The team processed the data, applied their speckle imaging techniques, and looked for any faint source near the expected position. There it was, a tiny point of light, roughly 6 magnitudes fainter than Betelgeuse, positioned at an angular separation of 52 milliarcseconds east of north. The location matched the dynamical predictions with remarkable precision. It was exactly where the models said a companion should be, at exactly the time the models said it should be visible. The detection was not overwhelming in statistical significance. The team reported it at roughly 1.5 sigma, which in normal circumstances would be considered tentative. But the alignment with prior predictions was striking. The companion appeared at the right position, the right time, the right brightness, and the right angular separation. Each of those independent agreements added weight to the detection beyond what the raw signal-to-noise ratio alone might suggest. The team characterized the companion as likely being about 1.6 solar masses, larger than some earlier estimates but consistent with a young, hot, pre-main sequence star of spectral type F, meaning it would glow with a blue-white color, utterly different from the deep red of its supergiant host. The companion was given a name. The discoverers proposed Siwarha, an Arabic word meaning her bracelet. The choice was deliberate and poetic. Betelgeuse's own name derives from an Arabic phrase, often translated as the hand of Al-Jaza, a reference to a female figure in Arabic astronomical tradition, a bracelet on the hand. The name was officially recognized by the International Astronomical Union's Working Group on Star Names in September 2025. What had been a hypothesis, then a candidate, now had an identity. But the discovery of Siwarha was not the end of the story. It was, in many ways, just the beginning. The detection showed that the companion existed. The next question was whether it was actually doing what theorists had predicted it was doing. Was Siwarha really interacting with Betelgeuse's atmosphere? Was it truly responsible for the mysterious secondary brightness cycle? Was it physically shaping the behavior of the supergiant? Answering those questions required a different kind of observation, not just spotting the companion, but tracking its influence over time. That answer came in January 2026, and it came from one of the most storied instruments in the history of astronomy. Andrea Dupree, the same Harvard astronomer who had led much of the surface mass ejection research, presented new results at the 247th meeting of the American Astronomical Society in Phoenix. Her team had combined nearly 8 years of observations from the Hubble Space Telescope with data from ground-based observatories at the Fred Lawrence Whipple Observatory and the Roque de los Muchachos Observatory. What they found was not just evidence that Siwarha existed. It was direct evidence that Siwarha was altering the physical environment around Betelgeuse in detectable, measurable ways. The key discovery was a wake. As Siwarha orbits Betelgeuse, it does not simply circle at a safe distance through empty space. It plunges through the supergiant's vast, extended outer atmosphere. Betelgeuse's atmosphere stretches far beyond what you might think of as the star's surface, an enormous envelope of gas that reaches outward for astronomical units. Siwarha's orbit, at roughly 4 astronomical units from Betelgeuse's center, places it squarely inside this extended atmosphere. As the companion moves through this tenuous material, it carves a path. Gas is disrupted, compressed, and stirred in its passage. A trail of denser material forms behind it, exactly like the wake left by a boat moving through water. Dupree's team detected this wake through careful spectroscopic analysis. They tracked changes in the specific wavelengths of light produced by different elements in Betelgeuse's atmosphere, and measured shifts in the speed and direction of gas flows in the outer layers. These changes showed a repeating pattern that aligned perfectly with the predicted orbital period of approximately 2,100 days. Every time Siwarha crossed in front of Betelgeuse, relative to our line of sight, the wake became detectable in the spectroscopic data. The trail of denser gas appeared, expanded outward, and gradually dissipated before the next orbital passage brought a fresh disturbance. The detection was elegant and decisive. It transformed Siwarha from a probable companion seen in a single tentative image into a confirmed physical actor in the Betelgeuse system. The companion was not just there, it was doing something. It was churning up the atmosphere of the supergiant with every orbit, leaving behind a swirling trail of disrupted material that Hubble and ground-based telescopes could track across years of patient observation. Dupree described the effect vividly. The companion creates a ripple effect in Betelgeuse's atmosphere that astronomers can actually see in the data. For the first time, they were seeing direct signs of the wake, confirming that Betelgeuse really does have a hidden companion shaping its appearance and behavior. The discovery resolved one of the most enduring puzzles surrounding the star. And that puzzle was the secondary brightness cycle. With the wake confirmed, the explanation became straightforward. Every 6 years, as Siwarha completes an orbit through Betelgeuse's outer atmosphere, the dense trail of gas it leaves behind absorbs and scatters some of the supergiant's light. This creates periodic changes in the brightness reaching Earth, changes that match the long-observed 2,100-day cycle. The secondary period was not caused by convective cells. It was not a second pulsation mode. It was the fingerprint of a tiny companion star dragging a curtain of disrupted gas through a giant's atmosphere once every 6 years. This realization fundamentally changed how astronomers interpreted Betelgeuse's recent history. Consider what this means for the Great Dimming. The surface mass ejection remains the primary explanation for the dramatic brightness drop of 2019 through 2020. The convective plume, the photospheric ejection, the dust cloud, all of that still holds, but the timing now looks different. The Great Dimming occurred near a minimum in the secondary cycle, meaning Siwarha's orbital effects may have been contributing additional variability on top of the intrinsic pulsation and the surface mass ejection. The coincidence of the primary 400-day pulsation minimum with the secondary cycle minimum may have amplified the dimming event beyond what either mechanism alone would have produced. Some researchers had already noted this suspicious alignment and speculated about it. The companion discovery provided the missing piece. The deepest dimming in nearly 2 centuries may have been partly a matter of unfortunate timing, multiple dimming mechanisms stacking on top of each other simultaneously. The companion also provided new context for Betelgeuse's mass loss behavior. Red supergiants shed material through stellar winds, and Betelgeuse's circumstellar environment is known to be complex, with multiple shells of expelled gas and dust detected at various distances from the star. Siwarha's repeated passage through the outer atmosphere stirs up material that might otherwise remain relatively quiescent. The companion could be enhancing dust formation, modulating the density of the circumstellar environment, and contributing to the episodic mass loss that characterizes Betelgeuse's late evolutionary stage. In other words, the companion is not just passively orbiting, it is actively participating in the processes that govern how the supergiant sheds its outer layers in preparation for its eventual death. The nature of Siwarha itself added another layer of fascination, based on the combined evidence from speckle imaging, spectroscopy, ultraviolet and X-ray observations. The companion appears to be a low-mass star, roughly 1.5 times the mass of our Sun. It is likely a young pre-main sequence star, meaning it has not yet fully settled into the stable hydrogen-burning phase that our Sun occupies. This is consistent with a star that formed alongside Betelgeuse roughly 10 million years ago, from the same molecular cloud, born as a sibling rather than a captured interloper. But while Betelgeuse, with its much greater mass, raced through its nuclear fuel and ballooned into a red supergiant, Siwarha evolved far more slowly. A star of 1.5 solar masses has a main sequence lifetime measured in billions of years. It is still in its stellar youth while its massive companion is approaching death. The orbital dynamics paint a dramatic picture of the future. Tidal interactions between the two stars are expected to gradually pull Siwarha inward. As Betelgeuse continues to expand and shed mass, the companion's orbit will decay. Current estimates suggest that Siwarha will be engulfed by Betelgeuse within approximately 10,000 years, swallowed whole by the supergiant's bloated atmosphere. Long before Betelgeuse goes supernova, its companion will have been consumed. The bracelet will be absorbed into the hand, but that future drama is secondary to what the companion means for the present. The confirmation of Siwarha provided astronomers with something they desperately needed: a concrete physical mechanism to explain behavior that had previously been attributed to vague internal processes. Before the companion was confirmed, every unusual brightness change, every spectroscopic anomaly, every unexpected shift in gas velocity had to be explained through the messy, poorly understood physics of convective envelopes and pulsation mode interactions. Now, a significant fraction of those variations could be attributed to a simple and well-understood mechanism: a small star orbiting inside a big star's atmosphere, stirring things up on a predictable schedule. This does not mean Betelgeuse is suddenly a solved problem. Far from it. The companion explains the secondary brightness cycle and provides context for some of the star's more puzzling atmospheric behavior. But it does not explain the surface mass ejection. It does not explain why the 400-day pulsation was disrupted for more than 2 years. It does not resolve the uncertainties in Betelgeuse's distance, mass, or evolutionary stage, and it introduces new questions of its own. How exactly does the companion interact with the convective plumes that drive the primary pulsation? Does its orbital passage trigger or suppress mass loss events? Could the interplay between Siwarha's wake and Betelgeuse's intrinsic variability produce effects that are more than the simple sum of two separate mechanisms? These questions matter because Betelgeuse is not just any star. It is the closest red supergiant to Earth and one of the most scientifically accessible massive stars in the final stages of evolution. Every observation of Betelgeuse contributes to our broader understanding of how massive stars evolve, shed mass, and eventually explode. The companion adds a new variable to an already complicated system, making the star simultaneously better understood and more challenging to model. The October 2025 findings from Carnegie Mellon University added yet another wrinkle. That team's observations suggested the companion star was not quite what earlier predictions had expected. Rather than a tiny, faint object at the end of its life, Siwarha appeared to be a somewhat larger and more luminous young star. This did not contradict the detection, but it refined the picture, hinting that the Betelgeuse system is more complex than even the companion hypothesis initially suggested. The properties of Siwarha affect how strongly it interacts with Betelgeuse's atmosphere, how much material it stirs up, and how detectable its effects are from Earth. Getting those properties right matters for every model built on the companion's influence. The next major observing opportunity will come in November 2027, when Siwarha is predicted to reach its widest apparent separation from Betelgeuse as seen from Earth. At that point, astronomers will have the best chance to study the companion with direct imaging techniques, potentially with instruments more sensitive than those used in the 2024 detection. Multiple observatories will train their instruments on the system, seeking to refine Siwarha's mass, temperature, luminosity, and orbital parameters. Each measurement will tighten the constraints on theoretical models and clarify how the companion shapes the supergiant's behavior. But even before 2027 arrives, the companion discovery has already reshaped the scientific narrative around Betelgeuse. For years, every unusual behavior from this star was filtered through a single dramatic question: is it about to explode? The great dimming fed that narrative. The brightness fluctuations fed it. The disrupted pulsation fed it. Media coverage amplified the supernova angle relentlessly, even when most scientists cautioned against it. The confirmation of Siwarha provides a powerful counterweight to that narrative. The long, mysterious secondary cycle was not a countdown to destruction. It was the signature of a companion star, a gravitational dance that has been going on for millions of years and will continue for thousands more. This does not eliminate the supernova question. Betelgeuse will still explode. That is not in doubt. But the companion discovery demonstrates that much of the behavior that excited public speculation and fueled dramatic headlines can be attributed to a process that is fascinating but not catastrophic. A small star carving a wake through a giant's atmosphere is remarkable, but it is not a death knell. What it is, though, is a reminder that even the most closely watched stars in the sky can harbour secrets that take decades of observation and multiple generations of instruments to uncover. Astronomers had been staring at Betelgeuse for centuries. They had measured its brightness, analysed its spectrum, modelled its pulsation, and mapped its circumstellar environment. And through all of that, a companion star was orbiting inside the atmosphere, invisible, influencing the data, shaping the observations, and evading detection until the right combination of predictions, instruments, and patience finally brought it into view. Siwarha was there the whole time. And now that scientists know what to look for, Betelgeuse's story has become richer, more complex, and far more interesting than the simple question of when it will blow up. But as we are about to see, even with the companion confirmed, Betelgeuse continues to challenge clean explanation. The star is better understood than it was 5 years ago. It is not yet understood well enough. It would be satisfying to end the story here. A massive star dimmed dramatically. Scientists figured out that a surface mass ejection caused it, and then they discovered a hidden companion that explained the long-standing secondary brightness cycle. Mystery solved, case closed. Move on to the next star. But Betelgeuse does not cooperate with tidy narratives. The companion discovery and the surface mass ejection analysis answered specific questions with remarkable clarity. They resolved puzzles that had persisted for years and even decades. And yet, step back from those individual answers and look at the full picture of what scientists actually know about this star, and what emerges is not a portrait of a well-understood object. What emerges is a portrait of a star that remains, in fundamental ways, deeply and stubbornly uncertain. The more astronomers learn about Betelgeuse, the more they realize how much they still cannot pin down. And that persistent uncertainty is, in many ways, the real reason scientists are worried right now. Start with the most basic question you can ask about any star. How far away is it? For most bright stars in the night sky, this question was settled decades ago. Modern instruments, particularly the European Space Agency's Hipparcos satellite in the 1990s and the Gaia mission beginning in 2013, have measured stellar distances with extraordinary precision. Gaia alone has catalogued parallax measurements for nearly 2 billion stars, nailing down their positions to fractions of a milliarc second. For the vast majority of nearby stars, the distance question is closed. The numbers are in the database, verified and reliable. Betelgeuse is not in that database. Not with useful precision, anyway. Gaia's instruments are designed for stars of moderate brightness. Betelgeuse is far too luminous. It saturates the detectors, overwhelming the sensitive optics that work beautifully on fainter targets. The result is that Gaia cannot produce a reliable parallax measurement for one of the most scientifically important stars in the sky. Betelgeuse was excluded from both Gaia Data Release 2 in 2018 and Data Release 3 in 2022. The most precise parallax measurement still available comes from the older Hipparcos mission, which placed Betelgeuse at a distance of roughly 643 light-years with a substantial margin of error. Other techniques have produced different estimates. Some studies, incorporating stellar modelling and evolutionary considerations, have suggested distances as low as roughly 400 light-years. Others cluster around 500 to 550. The commonly cited figure of approximately 650 light-years represents a reasonable middle ground, but the honest range spans from around 400 to over 600 light-years. For context, that is a spread of more than 50%. Imagine being told that a city you wanted to visit was somewhere between 400 and 600 miles away. The uncertainty would change your travel plans considerably. For Betelgeuse, the uncertainty changes everything. Distance is not just a number in stellar astronomy. It is the foundation on which virtually every other physical property is calculated. The luminosity of a star, its total energy output, is derived from its apparent brightness combined with its distance. Get the distance wrong, and the luminosity is wrong. Luminosity, in turn, feeds directly into calculations of the star's radius, its mass, its surface temperature, and its evolutionary stage. A Betelgeuse at 400 light-years is a significantly different physical object than a Betelgeuse at 650. It would be less luminous, probably less massive, and potentially at a different stage in its nuclear burning sequence. The models built on that distance would predict a different remaining lifetime, a different mass loss rate, and a different supernova outcome. This is not a hypothetical concern. A 2020 study led by Meredith Joyce at the Australian National University used the timing of Betelgeuse's pulsation modes to constrain its physical properties and concluded that the star might be closer and smaller than traditional estimates suggested. Their analysis favoured a distance of roughly 530 light-years, a current mass of around 16.5 to 19 solar masses, and a radius of about 764 times the Sun's radius. Other groups, using different methods and assumptions, have arrived at different answers. The lack of consensus on something as fundamental as distance means that every model of Betelgeuse is built on a foundation that could shift. Mass is equally problematic. The mass estimates we mentioned earlier, spanning from under 10 to over 20 solar masses, represent more than just imprecision. That is not a minor discrepancy. A star of 10 solar masses follows a substantially different evolutionary path than a star of 20. The mass determines the sequence and duration of nuclear burning stages in the core. It determines how much material remains in the core when fusion finally ceases. It determines whether the remnant left behind after the supernova is a neutron star or a black hole. And it determines the approximate timeline to the explosion itself. A more massive Betelgeuse burns through its fuel faster and has a shorter remaining lifetime. A less massive one lives longer. The difference between these scenarios spans tens of thousands of years, which might sound academic until you realize that it also changes the probability of the supernova occurring during any particular stretch of human history. The mass uncertainty is not just a matter of imprecise measurement, it reflects genuine physical complexity. Betelgeuse has been losing mass throughout its red supergiant phase, shedding material through stellar winds and episodic ejection events like the surface mass ejection of 2019. The rate at which this mass loss occurs affects the star's current mass, its remaining lifetime, and the nature of its eventual explosion. But mass loss rates for red supergiants are themselves poorly constrained. Different observational methods produce different estimates, and theoretical models of mass loss in these late evolutionary stages carry significant uncertainties. The surface mass ejection demonstrated that episodic events can eject as much material in a single blast as the steady stellar wind produces over an entire year. If such events occur regularly, the cumulative mass loss over thousands of years could be substantially higher than models based only on steady wind measurements would suggest. This connects to a deeper problem that extends well beyond Betelgeuse. Red supergiants in general are among the most difficult stars to model accurately. They are enormous, with extended, tenuous atmospheres that defy simple physical descriptions. Their surfaces are not smooth and well-defined like the Sun's photosphere. Instead, they are dominated by a small number of giant convective cells, massive upwellings and downwellings of hot and cool material that create a roiling, constantly shifting surface. Direct images of Betelgeuse's surface, captured by instruments like the sphere camera on the Very Large Telescope, show this dramatically. The star's disk is not a uniform circle. It is mottled, asymmetric, with bright and dark patches that change over time as convective cells rise, evolve, and sink. These convective cells are not just surface features. They extend deep into the star's interior, connecting the outer atmosphere to the nuclear burning shells below. Modeling them accurately requires three-dimensional hydrodynamic simulations that push the limits of current computational resources. The challenge is that convection in a red supergiant does not behave like convection in smaller stars. In the Sun, millions of small convective granules churn across the surface, each one perhaps 1,000 kilometers across. The overall effect is relatively smooth and predictable when averaged over large areas. In Betelgeuse, the convective cells are so large that only a handful fit on the visible surface at any given time. Each cell spans a substantial fraction of the star's diameter. This means that individual convective events can have global consequences. A single massive plume rising from the interior can brighten an entire hemisphere, alter the spectral signature of the whole star, and even trigger mass ejection events. The surface mass ejection of 2019 was likely caused by exactly such a plume, a convective upwelling more than 1 million miles across that produced shocks powerful enough to blast off a piece of the photosphere. This inherent turbulence creates a problem for astronomers trying to separate different physical effects. When Betelgeuse's brightness changes, is the cause a pulsation cycle, a convective event, the passage of Siwarha through the atmosphere, or some combination of all three? The answer, frustratingly often, is that all of these processes are happening simultaneously, and they interact in ways that are not yet fully understood. The companion's wake stirs up gas that may interact with convective plumes. Pulsation-driven expansion and contraction changes the density of the atmospheric material through which Siwarha moves. Convective events can trigger mass loss episodes that alter the circumstellar dust environment, which in turn affects how much light reaches Earth. The system is coupled and dynamic, with multiple processes feeding back on each other in a tangle that resists clean analytical separation. This is why the companion discovery, as significant as it is, did not simply solve Betelgeuse. Siwarha explains the secondary brightness cycle beautifully, but the star's behavior is not just the sum of two neat periodic signals. It is a complex nonlinear interaction of pulsation, convection, mass loss, and orbital dynamics, all occurring inside a star whose basic parameters remain uncertain. Scientists can explain specific phenomena, the secondary cycle, the great dimming, the disrupted pulsation, but they cannot yet produce a single unified model that consistently reproduces everything Betelgeuse does over time. The aftermath of the surface mass ejection illustrates this difficulty. The disruption of the 400-day pulsation cycle was one of the most striking consequences of the 2019 event. For more than 2 years, the familiar rhythm vanished from the data. When signs of recovery began to appear, the oscillations initially showed up at twice the original frequency, a transient response that researchers expected would eventually settle back into the fundamental mode. But the recovery was not smooth. Betelgeuse's brightness and radial velocity measurements showed irregular fluctuations that did not fit neatly into any single pulsation model. The star was rebuilding its internal rhythm, but the process was messy and protracted. Then, in late 2023, Betelgeuse did something unexpected again, but this time in the opposite direction. The star surged in brightness, climbing to approximately magnitude 0, significantly brighter than its recent average. For a brief period, it rose to become roughly the 7th brightest star in the entire night sky, noticeably more luminous than it had been in years. If the Great Dimming represented an unprecedented drop, The 2023 brightening represented an unusual spike, and it arrived at a time when the star's behavior was supposed to be settling back toward normalcy after the surface mass ejection. The brightening reignited public speculation about an imminent supernova, just as the Great Dimming had 3 years earlier. Once again, headlines appeared suggesting Betelgeuse might be about to explode. Once again, most professional astronomers cautioned that brightness variations, even unusual ones, are not reliable indicators of core collapse. But the episode was scientifically significant, regardless of whether it had anything to do with the star's eventual death. It demonstrated that Betelgeuse was still producing behavior that fell outside the expected range. The pulsation was supposed to be recovering. The star was supposed to be settling down. Instead, it brightened to a level that had not been seen in recent observing history. The cause of the 2023 brightening remains debated. Some researchers attributed it to a particularly vigorous convective upwelling that temporarily increased the photospheric temperature across a large fraction of the visible surface. Others suggested it might reflect the ongoing recovery from the surface mass ejection, with the star's pulsation overshooting its equilibrium brightness as the internal oscillations re-establish themselves. The companion adds yet another possibility. If Siwarha's orbital position at that time placed its atmospheric wake away from the line of sight between Betelgeuse and Earth, the absence of the wake's dimming effect could allow the star to appear brighter than during phases when the wake partially obscures its light. Disentangling these possibilities requires precisely the kind of multivariable modelling that remains beyond current capabilities. The 2023 brightening joined the growing list of Betelgeuse events that can be described but not yet definitively explained. Some of the pulsation irregularity might also be attributable to the companion. Siwarha's orbital passage disrupts the atmospheric material through which pulsation waves propagate. If the pulsation is trying to re-establish itself while the companion is simultaneously stirring up the outer layers, the two effects could interfere with each other, producing the kind of erratic behavior that observers documented. But this hypothesis, while plausible, has not been rigorously tested against the data. Separating Siwarha's influence from the ongoing pulsation recovery requires disentangling two periodic signals of different timescales that are both embedded in a noisy background of convective variability. It is a signal processing challenge of considerable difficulty. The circumstellar environment adds yet another layer of complexity. Betelgeuse is surrounded by multiple shells and arcs of expelled material at various distances from the star. These structures, detected through infrared and radio observations, record the history of mass loss over thousands of years. Some of the material was ejected by stellar winds. Some may have been produced by past surface mass ejection events, assuming the 2019 event was not a unique occurrence. And some may have been influenced by Siwarha's orbital dynamics, with the companion stirring up material that was then expelled more easily into the circumstellar environment. Understanding this environment matters because it affects observations of the star itself. Dust between Betelgeuse and Earth dims and reddens the star's light. The amount and distribution of circumstellar dust changes over time as new material is ejected and older material disperses. This means that the apparent brightness of Betelgeuse is not just a function of what the star itself is doing, it is also a function of what the material around the star is doing. Separating intrinsic variability from circumstellar effects requires multi-wavelength observations that probe different layers of the system: optical light for the photosphere, ultraviolet for the chromosphere, infrared for the dust, and radio for the extended gas environment. Modern observatories can do this, and they have. But even with data spanning the electromagnetic spectrum from multiple world-class facilities, the picture remains incomplete. Each wavelength reveals a different aspect of the Betelgeuse system, and fitting all those aspects into a single coherent model is a problem that has occupied researchers for decades without a fully satisfying solution. This might seem like a failure of science, but it is actually the opposite. Betelgeuse's persistent complexity is scientifically invaluable, precisely because it exposes the limitations of current models. Red supergiants are critically important objects in astrophysics. They are the immediate progenitors of core collapse supernovae. The explosions that produce neutron stars and black holes forge heavy elements like iron, gold, and platinum, and inject energy and enriched material into the interstellar medium. Every atom of carbon in your body, every atom of oxygen you breathe, was manufactured inside a star that once looked something like Betelgeuse. The elements were scattered into space when that star exploded. Understanding how red supergiants behave in the final stages before the explosion is essential for understanding the cosmic processes that make planets, chemistry, and life possible. But here is the problem. Betelgeuse is the only red supergiant close enough and large enough to study in this kind of detail. Other red supergiants exist. Antares in Scorpius is the next most prominent example, but none of them offer the combination of size, proximity, and brightness that makes Betelgeuse so uniquely accessible. Betelgeuse was the first star other than the Sun to be directly imaged, back in 1996 when the Hubble Space Telescope captured its disk and revealed hotspots on the surface. Even today, it remains one of the very few stars whose surface features can be directly imaged. This means that essentially all of our detailed observational knowledge about the surfaces, atmospheres, and circumstellar environments of red supergiants comes from a single object. That is an extraordinarily narrow foundation on which to build a general understanding of how massive stars die. If Betelgeuse is somehow atypical, if its mass loss behavior, its convective dynamics, or its companion interactions make it unusual among red supergiants, then the models we build from its observations might not apply well to the broader population. Conversely, if Betelgeuse is representative, then the complexity and uncertainty we encounter in studying it suggest that our models of all red supergiants are significantly oversimplified. The companion discovery highlights this tension. Before Siwarha was confirmed, models of Betelgeuse's variability had to explain everything through intrinsic processes: pulsation, convection, mass loss. Now we know that an external perturber has been influencing the data all along. How many other red supergiants might have undetected companions altering their observed behavior? Binary and multiple star systems are common in the galaxy. More than half of all Sun-like stars have at least one companion. For massive stars, the fraction is even higher. It is entirely plausible that other red supergiants are orbited by companion stars, whose effects are currently misinterpreted as intrinsic variability. This has implications for supernova predictions. One of the long-standing goals of stellar astrophysics is to identify observational signatures that indicate a massive star is approaching the final stages before explosion. Changes in brightness, pulsation period, mass loss rate, and surface temperature have all been proposed as potential pre-supernova indicators. But if companion interactions can mimic or modulate these same signatures, the diagnostic power of any single indicator is weakened. An unusual brightness change might signal approaching core collapse, or it might signal the passage of a companion through the extended atmosphere. Without knowing whether a companion exists, interpreting the observation becomes ambiguous. Betelgeuse also challenges models in a more fundamental way. The star is a runaway. Observations show that it is moving through the interstellar medium at approximately 30 kilometers per second, fast enough to have been ejected from its birth association in the Orion OB1 group, the region of hot young stars that includes the 3 stars of Orion's belt. Runaway stars are typically produced by dynamical interactions in dense stellar environments, either through close encounters with other stars that gravitationally sling one member out of the system, or through the supernova explosion of a binary companion whose death kick sends the surviving star flying. This velocity is not just an entry in a catalogue. It has physical consequences that are directly observable. Betelgeuse is ploughing through the interstellar medium so fast that it creates a bow shock, a curved wave of compressed gas and dust piled up ahead of the star like the wake in front of a speeding boat. This bow shock is enormous. It stretches roughly 4 light-years across, a structure so vast that if you placed it at the distance of Alpha Centauri, it would span most of the gap between our Sun and the nearest star. The bow shock was detected in infrared observations, glowing faintly as the compressed interstellar material is heated by the collision. Behind the bow shock, extending away from the star's direction of motion, trails a complex structure of expelled material, gas and dust, shed by Betelgeuse's stellar wind over thousands of years, now left behind as the star races onward. The bow shock is more than a visual curiosity. Its shape and size depend on the balance between the ram pressure of the star's motion through the interstellar medium and the pressure of the stellar wind pushing outward. Measuring the bow shock's geometry provides independent constraints on Betelgeuse's mass loss rate and wind velocity, but those constraints depend on knowing the density of the local interstellar medium, which is itself uncertain. So even this dramatic, directly observable structure becomes another variable in the web of interconnected uncertainties that defines Betelgeuse research. The bow shock tells us something about the star's mass loss, but only if we know the properties of the material it is crashing through, and the properties of that material are not known with precision. If Betelgeuse was ejected by a companion supernova, that adds another dimension to the star's history. It would mean Betelgeuse once had a more massive binary partner that already exploded, possibly enriching Betelgeuse's atmosphere with heavy elements and altering its rotational dynamics. This is distinct from the Siwarha companion, which is a smaller, younger star that would not have been involved in a prior supernova event. The runaway velocity and the current companion may be entirely separate aspects of Betelgeuse's history, each adding complexity to a system that was already difficult to model. Rotation is another poorly constrained parameter. Betelgeuse rotates slowly, with a measured surface velocity of about 5.5 kilometers per second, giving it a rotation period of approximately 36 years at its current size. The rotation axis appears to be inclined at roughly 60 degrees to our line of sight. Both of these values carry significant uncertainty, and they matter because rotation affects how material mixes inside the star, how convective cells organize on the surface, and how the star loses angular momentum through its stellar wind. Changes in rotation rate could affect pulsation properties, mass loss patterns, and the distribution of heavy elements in the outer layers. All of these feed into evolutionary models that attempt to predict the star's remaining lifetime and eventual supernova characteristics. Magnetic fields add yet another poorly understood factor. In 2010, spectropolarimetric observations detected a weak magnetic field on Betelgeuse's surface. The role of magnetic fields in red supergiant evolution is not well established, but theoretical work suggests that even moderately strong fields could influence dust formation, wind dynamics, and mass loss rates. If magnetic fields interact with convective plumes, or if they channel outflowing material in preferential directions, they could contribute to the asymmetric structures observed in Betelgeuse's circumstellar environment. The cumulative effect of all these uncertainties is that Betelgeuse remains, despite centuries of observation and decades of intensive study with modern instruments, a star that defies complete and confident characterization. Scientists know a great deal about it. They know it is a red supergiant. They know it pulsates. They know it has a companion. They know it experienced a surface mass ejection of unprecedented scale. They know it will eventually explode. But when you push past these established facts and ask more precise questions, how massive is it exactly? How far away is it exactly? How does its internal convection couple to its pulsation and mass loss? How does the companion interact with intrinsic variability? The answers dissolve into ranges, estimates, and competing models. This is the real source of scientific concern. When astronomers say they are worried about Betelgeuse, they do not mean they are lying awake at night expecting an explosion. They mean that one of the most important objects in stellar astrophysics, a star that serves as the primary observational laboratory for understanding the final evolutionary stages of massive stars, continues to produce surprises that expose the gaps in current understanding. The Great Dimming was a surprise. The companion was a surprise. The disrupted pulsation was a surprise. The anomalous brightening of 2023 was a surprise. Each surprise was eventually given a plausible explanation, but each explanation raised new questions that have not yet been answered. The worry is not that the star will explode tomorrow. The worry is that the star is telling us something about the physics of red supergiant evolution that we are not yet equipped to fully understand. And since red supergiants are the stars that produce the supernovae that seed the universe with the heavy elements necessary for planets and life, what we do not understand about Betelgeuse is, in a very real sense, something we do not understand about the cosmic processes that made our own existence possible. Every new instrument that observes Betelgeuse reveals new layers of complexity. Every new dataset raises questions alongside the answers it provides. The star cooperates just enough to keep scientists coming back, offering tantalizing clues about its nature, then retreating behind walls of noise, uncertainty, and physical intricacy that prevent a final, definitive characterization. Betelgeuse is not a solved problem. It is an ongoing investigation, and the next step in that investigation, the one that addresses the question everyone really wants to ask, depends entirely on how honestly we confront what we still do not know. There is a question that has been hovering over this entire story, the question that brought most of you here in the first place, the question that generates headlines and social media speculation every time Betelgeuse does anything unexpected. Will it explode? And if so, when? The honest answer is both simple and deeply unsatisfying. Yes, Betelgeuse will explode. That is not speculation, not hypothesis, not a matter of scientific debate. A star of this mass, at this evolutionary stage, burning through the final sequences of nuclear fuel in its core, has exactly one possible endpoint: core collapse, supernova. The physics is settled. Betelgeuse will die in one of the most violent events the universe can produce. But when? That is where honesty becomes uncomfortable. The best current estimate, based on the full range of stellar evolutionary models and the admittedly uncertain physical parameters of the star, is that Betelgeuse will go supernova sometime within the next 100,000 years. That is not a typo. 100,000 years. The window is so wide that it encompasses the entire span of recorded human history more than 10 times over. It could happen tomorrow. It could happen when our descendants have colonized other star systems, assuming we survive that long. It could have happened already, 650 years ago, with the light from the explosion still racing toward us through the void, not yet arrived. Some researchers have tried to narrow this window. A 2023 paper generated significant attention by suggesting that Betelgeuse might be in the late stages of carbon burning in its core, which would place the supernova on a timescale of tens of years rather than tens of thousands. The paper, titled "The Evolutionary Stage of Betelgeuse, Inferred from its Pulsation Periods," used the star's observed pulsation characteristics to constrain which nuclear burning phase it currently occupies. If the pulsation periods correspond to a star that has already progressed through helium and carbon burning and is approaching the final stages of neon or oxygen fusion, then the remaining lifetime could be dramatically shorter than the standard estimate. The paper attracted enormous public interest, which is understandable. The idea that the nearest red supergiant might explode within a human lifetime is irresistible. But the broader stellar evolution community received the claim with considerable skepticism. The analysis depends heavily on the assumed mass, distance, and internal structure of the star, all of which remain uncertain. Different assumptions about these parameters lead to different conclusions about the current burning stage. Most specialists in massive star evolution continue to favor the longer timescale, placing the supernova most likely within the next 100,000 years rather than the next few decades. The uncertainty in Betelgeuse's fundamental properties simply does not allow the kind of precision needed to narrow the window to tens of years with any confidence. This ambiguity is itself revealing. It underscores the central theme of this story. Even for the most studied red supergiant in the sky, the star whose surface has been directly imaged, whose companion has been detected, whose mass ejection has been documented in real time, we cannot determine the remaining lifetime to better than 5 orders of magnitude, somewhere between tomorrow and 100,000 years. That is a humbling range for a civilization that can measure the age of the universe to within a fraction of a percent. To appreciate why the timing is so difficult to predict, it helps to think about the pacing of those final nuclear burning stages we described earlier. We already know that each successive phase is shorter than the last, that the clock accelerates from millions of years down to a single day of silicon fusion before the iron core forms. But what matters for prediction is not the pacing itself. It is where the boundary of visibility falls. Carbon burning, which lasts perhaps 1,000 years, represents approximately the last stage where astronomers might hope to constrain the timeline through indirect observational signatures. Everything after carbon happens too fast and too deep to detect from outside. After carbon, the star enters a phase of terminal acceleration that is completely hidden from view. The final year of neon burning, the final months of oxygen burning, the final day of silicon fusion, all of it occurs in the innermost core, shielded by hundreds of solar radii of opaque stellar material. No photon from those reactions reaches the surface. No change in luminosity or temperature betrays what is happening below. Within seconds of the iron core reaching a critical mass, roughly 1.5 times the mass of the Sun packed into a volume the size of Earth, the core collapses at roughly 1/4 of the speed of light. The implosion triggers a bounce, a rebound shockwave that reverberates outward through the falling material, and eventually, aided by an enormous flood of neutrinos, blows the star apart. This hiddenness is the central problem. The star's surface, that vast red supergiant photosphere stretching outward for astronomical units, is completely decoupled from the core's final drama. The surface temperature does not change appreciably during the transition from one late burning stage to the next. The luminosity does not shift in any diagnostic way. The pulsation behavior is driven by the envelope, not by what is happening at the center. An astronomer observing Betelgeuse on the last day of silicon burning would see a star indistinguishable from one still centuries away from collapse. There is no warning. The only signal comes when the core has already collapsed and the neutrinos are already on their way. This is why no astronomer can tell you when Betelgeuse will explode. It is not a matter of needing better telescopes or more data. It is a fundamental limitation. The information we need, the current composition and burning stage of the innermost core, is physically inaccessible. It is locked inside the densest, hottest region of the star, unreachable by any electromagnetic observation. The only messenger that could carry that information to us before the explosion is the neutrino, and neutrinos from the normal burning stages are too few and too low in energy to detect at interstellar distances. We will know Betelgeuse's core has collapsed only when millions of neutrinos hit our detectors in a 10-second burst. At that point, the star is already dead. The light show follows hours later. But suppose it does happen. Suppose the core of Betelgeuse collapses while we are still around to witness it. What would we see? The first signal would not be light. It would be neutrinos. When a massive star's iron core collapses, the implosion produces an extraordinary flood of neutrinos, subatomic particles that interact so weakly with matter that they pass through the collapsing star itself almost unimpeded. These neutrinos would race outward from the core at nearly the speed of light, arriving at Earth several hours before any visible light from the explosion. We know this because it happened before. In 1987, a supernova erupted in the Large Magellanic Cloud, a satellite galaxy roughly 168,000 light-years away. 3 small neutrino detectors operating at the time registered a total of about 24 neutrinos from the event. 24 particles, from an explosion 168,000 light-years distant. That detection confirmed decades of theoretical predictions about how core collapse supernovae work. Today, the neutrino detection infrastructure is incomparably more capable. Facilities like IceCube at the South Pole, Super Kamiokande in Japan, and numerous other detectors around the world are orders of magnitude more sensitive than what existed in 1987. And Betelgeuse is roughly 260 times closer than that 1987 supernova was. The inverse square law means the neutrino flux at Earth would be roughly 70,000 times stronger. Instead of detecting 24 neutrinos, modern observatories would register millions, perhaps tens of millions, in a burst lasting 10 to 15 seconds. The signal would be unmistakable, a screaming alarm in every neutrino detector on the planet, announcing that a star 650 light-years away had just died. An international system called the Supernova Early Warning System, or SNEWS, already exists for exactly this scenario. It links neutrino detectors around the world into a network that automatically triggers an alert when multiple facilities register a simultaneous burst. The alert would go out to observatories worldwide within minutes, giving astronomers a precious window of several hours to train every available telescope on Betelgeuse before the visible fireworks begin. It would be the most anticipated astronomical observation in history, a supernova announced in advance by the particles from its own death. For a few hours after the neutrino burst, nothing visible would happen. The shock wave from the collapsing core would still be propagating outward through the star's interior, ploughing through layers of silicon, oxygen, carbon, helium, and hydrogen. The star's surface would show no sign of what was happening deep inside. Observers watching Betelgeuse through telescopes during those hours would see a perfectly normal red supergiant. But underground, in laboratories around the world, physicists would be racing to analyze the neutrino data, already knowing that the sky was about to change. Then the shock wave would reach the surface. The breakout, as astrophysicists call it, would produce a sudden, intense flash of ultraviolet and X-ray radiation as the superheated shock front ripped through the photosphere and into space. Within hours, the visible brightness would begin climbing, and it would climb fast. At peak luminosity, a Betelgeuse supernova would shine approximately as bright as the half moon. Not as bright as the full moon, which is a common exaggeration, but roughly comparable to a half moon. That is still astonishingly bright for a single point of light. It would be easily visible during the daytime, a brilliant pinprick in the blue sky near the constellation Orion. At night, it would cast shadows. You could read by its light. It would dominate the sky in a way no star has done since the Crab Nebula supernova of 1054, and it would be significantly closer and brighter than that event was. That comparison to historical supernovae is worth pausing on. Humanity has a surprisingly thin record of witnessing stellar explosions within our own galaxy. Chinese astronomers recorded a brilliant guest star in the year 1054 that was visible in daylight for 23 days and remained visible to the naked eye for nearly 2 years. The remnant of that explosion is the Crab Nebula, roughly 6,500 light-years away, 10 times farther than Betelgeuse. In 1572, the Danish astronomer Tycho Brahe observed a new star in the constellation Cassiopeia that rivaled Venus in brightness. That supernova, roughly 10,000 light-years distant, helped dismantle the ancient belief that the heavens were fixed and unchanging. In 1604, Johannes Kepler observed the last supernova visible to the naked eye in our galaxy, in the constellation Ophiuchus, roughly 20,000 light-years away. That was more than 4 centuries ago. No supernova has been observed within the Milky Way since, not with the naked eye and not with any telescope ever built. 422 years. That is how long it has been since a human being witnessed a supernova in our home galaxy. Every advance in astronomical instrumentation, every major telescope built, every detector conceived and constructed, none of them have ever been turned on a galactic supernova in real time. Our understanding of core collapse explosions comes entirely from studying supernovae in other galaxies, millions of light-years away, where the events appear as tiny points of light in distant systems. A Betelgeuse supernova would be the first time in the history of science that humanity observed a nearby stellar explosion with the full power of modern technology. The data would be transformative in ways that are difficult to overstate. The spectacle would last for months. Peak brightness would persist for several weeks before the supernova began to fade. Over the following months, the light would gradually diminish. but the object would remain visible to the naked eye for the better part of a year. Orion would look permanently altered, its familiar shoulder replaced by a blazing point of light that would slowly wane over the course of seasons. Eventually, over years and decades, the expanding remnant would become a diffuse nebula visible through telescopes, a glowing scar in the sky where a star used to be. The question that inevitably follows is whether we should be afraid. The answer, supported by every relevant calculation, is no. Betelgeuse is too far away to harm Earth. The dangerous effects of a supernova, intense radiation, high-energy particles, blast waves, all diminish with the square of the distance. Studies have estimated that a supernova would need to occur within roughly 160 light-years of Earth to pose a genuine threat to the biosphere. Betelgeuse is approximately 4 times farther away than that danger threshold. The explosion would be spectacular, historically unprecedented in the era of modern science, and completely harmless. No increase in radiation exposure, no disruption of the atmosphere, no mass extinction. Just the most extraordinary light show any living human has ever witnessed. For professional astronomers, the event would be a once-in-a-civilization scientific windfall. No galactic supernova has ever been observed with modern instruments. Not with spectroscopes, not with radio dishes, not with X-ray satellites, not with neutrino detectors. A Betelgeuse supernova would provide an unprecedented opportunity to study every phase of a core collapse explosion in real time, across every wavelength from radio to gamma rays, with gravitational wave detectors, neutrino observatories, and space telescopes all trained on a single event happening in our cosmic backyard. The scientific return would be incalculable. Entire careers would be built on the data, textbooks would be rewritten. Our understanding of how massive stars die, how neutron stars or black holes form, how heavy elements are forged and dispersed into the interstellar medium, all of it would advance by decades in a matter of months. But all of this is contingent on timing, and the timing, as we have established, is unknowable. Betelgeuse could explode tonight. It could explode after every person alive today has been dead for 10,000 generations. There is no observational signature that reliably predicts the final collapse more than hours in advance. The neutrino burst is the only confirmed precursor, and it arrives only hours before the light. By the time we know it is happening, it is already done. This brings us to Siwarha and what the companion's future tells us about the system as a whole. Current models predict that tidal interactions will gradually drag Siwarha inward toward Betelgeuse. As the supergiant continues to evolve, its outer layers will expand further, and the companion's orbit will decay. Within approximately 10,000 years, Siwarha is expected to be engulfed entirely, pulled into the body of the red supergiant and consumed. The bracelet will disappear into the hand that wears it. This engulfment would itself be a dramatic event, though nothing compared to a supernova. As Siwarha spirals inward and enters the denser layers of Betelgeuse's atmosphere, the interaction would release gravitational energy, heat the surrounding material, and potentially trigger enhanced mass loss or outbursts. The final absorption might produce observable effects from Earth, though predicting exactly what those effects would look like requires modelling capabilities that do not yet exist for systems this complex. The important point is the timeline. Siwarha is expected to be engulfed in roughly 10,000 years. Betelgeuse is expected to go supernova in roughly 100,000. If both estimates are correct, the companion will be long gone before the explosion occurs. The star will die alone, having already consumed its closest neighbour. But these timelines carry their own large uncertainties, and the possibility that the engulfment and the supernova might be separated by less time than currently estimated cannot be ruled out. If the companion's inward spiral accelerates due to factors not yet modelled, or if the supernova timeline is shorter than the standard estimate, the two events could be closer together than current predictions suggest. The next major observing opportunity for the Siwarha system will come in November 2027, when the companion is predicted to reach its widest apparent separation from Betelgeuse as seen from Earth. At that point, astronomers will have the best geometry for direct imaging and spectroscopic characterization. Multiple observatories are already planning dedicated observation campaigns for that window. The goal is to refine Siwarha's mass, temperature, luminosity, and orbital elements with much greater precision than the current tentative detection allows. Each improvement in these parameters will tighten the constraints on how the companion interacts with the supergiant and how the system will evolve in the coming millennia. But 2027 is not the only milestone on the observational horizon. Several next-generation instruments and facilities are poised to study Betelgeuse with capabilities that did not exist even a few years ago. The James Webb Space Telescope, already the most powerful infrared observatory ever launched, can observe the material ejected during the 2019 surface mass ejection as it continues drifting away from the star. That dust cloud is still out there, expanding and cooling, carrying information about the composition and physics of the ejection event encoded in its infrared emission. Webb's sensitivity at these wavelengths far exceeds anything previously available. Detailed spectroscopy of the ejected material could reveal what fraction of Betelgeuse's photosphere was removed, what elements it contained, and how the dust grains formed as the material cooled. Each of these measurements feeds back into models of mass loss, dust production, and circumstellar environment evolution that are central to understanding late-stage stellar physics. On the ground, the Vera C. Rubin Observatory, with its legacy survey of space and time, will begin a decade-long survey of the entire visible sky every few nights. While Betelgeuse itself is too bright for the survey's primary science goals, the observatory's cadence and coverage will provide continuous, systematic monitoring of the star's brightness with a consistency that no previous facility has achieved. More importantly, Rubin's survey will discover and characterize thousands of variable stars and transient events across the galaxy, providing a statistical context for Betelgeuse's behavior. If surface mass ejections turn out to be common among red supergiants, Rubin has the best chance of catching them on other stars, offering comparative data that Betelgeuse alone cannot provide. The next generation of extremely large telescopes currently under construction, including the extremely large telescope being built by the European Southern Observatory in Chile, will bring angular resolution capabilities that surpass anything available today. These instruments will be able to resolve finer details on Betelgeuse's surface, track the motion of convective cells with greater precision, and potentially image Siwarha directly during favorable orbital geometry, without relying on the specialized speckle imaging techniques that produce the current tentative detection. The ability to routinely image a red supergiant's surface at high resolution will transform Betelgeuse from a star observed in snapshots into a star observed in continuous, detailed motion. And quietly, steadily, neutrino observatories around the world continue their vigil. Detectors like IceCube, Super Kamiokande, the Sudbury Neutrino Observatory successor, and newer facilities like the Jiangmen Underground Neutrino Observatory in China stand ready to catch the burst that would signal the end. The Supernova early warning system links them together, ensuring that when the moment comes, whether tonight or in 10,000 years, the alert will go out and the scientific community will have its precious hours of advance notice. These detectors do not sleep. They do not take nights off. They watch, patiently, for a signal that might never come in our lifetimes, but that physics guarantees will come eventually. But stepping back from the specific scientific questions, there is a larger significance to the Betelgeuse story that deserves reflection. This star has become something rare in modern astronomy. It has become a laboratory where the unknown is not hidden behind billions of light years of distance or billions of years of cosmic time. It is right there, 650 light years away, glowing in the shoulder of Orion, visible to anyone who steps outside on a clear winter night and looks up. The mysteries of Betelgeuse are accessible in a way that most cosmic mysteries are not. You can see the object of study with your own eyes. You can point at it and say, "That is the star that tore off a piece of its own surface and hurled it into space. That is the star with a hidden companion carving a wake through its atmosphere. That is the star that will someday produce one of the most spectacular events any human will ever witness. And yet, for all that accessibility, for all the centuries of observation and the decades of modern study, Betelgeuse continues to surprise. It continues to reveal behavior that was not predicted, that challenges existing models, that forces scientists to revise their assumptions and expand their understanding. This is not a failure of the scientific process. It is the scientific process working exactly as it should. Nature is under no obligation to conform to our models. When observations contradict predictions, the models must change. And Betelgeuse has forced more model revisions in the past 6 years than most stars produce in a century. None of the major discoveries of the past 6 years were anticipated by the models that existed before them. The theoretical framework for red supergiant evolution contained no mechanism for a star to eject a chunk of its own photosphere in a single violent episode. The models that explained Betelgeuse's secondary brightness cycle relied entirely on intrinsic processes, convection or pulsation mode interactions, with no provision for an external companion orbiting inside the atmosphere. The understanding of stellar pulsation assumed that a 400-day fundamental mode, once established, would persist until the star's death, not that it could be shut down for years by a surface eruption. In every case, the observation came first and the explanation followed. The models did not lead. They were dragged. This pattern of reactive understanding expanded the space of what astronomers considered possible for red supergiants. Each one added new variables to an already complicated system. And each one came from the same star, the one we know best, the one we have studied the longest, the one closest to Earth. If this star, the single most observed red supergiant in the sky, can still produce fundamental surprises, what does that say about the thousands of other red supergiants scattered through our galaxy? Stars that are too distant for surface imaging, too faint for high-cadence spectroscopic monitoring, too obscured by intervening dust for detailed characterization? How many of them harbor unseen companions? How many of them have experienced surface mass ejections that went unrecorded because no one was watching closely enough? How many of them are behaving in ways that would challenge our models if only we could see them clearly? This is the question that gives Betelgeuse its deepest scientific significance. It is not just one interesting star. It is a window into an entire class of objects that we understand far less well than we would like to believe. Red supergiants are the final act in the lives of massive stars. They are the precursors to the explosions that forge heavy elements, create neutron stars and black holes, and shape the chemical evolution of galaxies. Getting the physics of red supergiants right is essential for understanding supernovae, and getting supernovae right is essential for understanding the origin of the elements that make up planets, atmospheres, oceans, and living organisms. The stakes are not abstract. They are about the fundamental processes that connect stellar death to the chemistry of existence. And right now, the best laboratory we have for studying those processes is a single, complicated, surprising, maddeningly uncertain star in Orion. That star has told us more about late-stage stellar evolution in the past 6 years than many researchers expected to learn in a career, but it has also shown us how much remains unknown. The surface mass ejection revealed a mass loss mechanism that had never been directly observed. The companion revealed an external influence that had been misinterpreted for decades. The pulsation disruption revealed a fragility in a process that had seemed permanent and stable. Each discovery was a triumph of observation. Each discovery was also a reminder of how much our models were missing. When scientists say they are worried about Betelgeuse, this is what they mean. The worry is not that the star will explode and harm us. It will not. The worry is not that a supernova is imminent. It almost certainly is not, at least not on any timescale relevant to anyone alive today. The worry is something more subtle and more profound. It is the recognition that one of the most famous, most visible, most intensely studied stars in the entire sky is still capable of revealing behavior that no one predicted and that existing models cannot fully explain. That kind of worry is not anxiety. It is the productive discomfort that drives science forward. It is the awareness that the universe is more complex than our equations currently capture, and that the gap between observation and understanding is wider than we might wish. Every surprise Betelgeuse produces is an invitation to build better models, develop more sensitive instruments, and ask sharper questions. Every anomaly is a clue, a fingerpost pointing toward physics that has not yet been written into the textbooks. And so astronomers continue to watch. They monitor the star's brightness with ground-based photometry. They track its spectral changes with high-resolution spectrographs. They resolve its surface features with interferometric imaging. They model its interior with three-dimensional hydrodynamic simulations. They wait for Siwarha to emerge into better viewing geometry in 2027. They wait for the James Webb Space Telescope to reveal new details about the ejected material still drifting away from the star. They wait for the next generation of enormous ground-based telescopes to bring Betelgeuse's surface into sharper focus than ever before. They wait, above all, for the next surprise. Because if the past 6 years have taught them anything, it is that Betelgeuse will provide one. Look up on a clear winter night and find Orion. Find the bright orange-red star at the hunter's shoulder. It has been there for as long as humans have looked at the sky. Ancient Egyptians tracked it. Greek astronomers named the constellation around it. Arabic scholars gave it the name we still use today. For millennia, it was simply a bright star, beautiful and constant, a fixed point in the turning sky. It is not constant. It never was. It is a dying giant, shedding its skin, shaking from internal convulsions, orbited by a companion it will eventually swallow, destined for an explosion that will outshine every other star in the galaxy for weeks. It is a star in the grip of processes so complex that even now, with every telescope humanity can muster aimed in its direction, we cannot fully describe what is happening inside it. We cannot say when it will die. We cannot predict what it will do next. And that uncertainty, that irreducible gap between what we can observe and what we can explain, is not a limitation to be ashamed of. It is the frontier. It is where science lives, in the space between what we know and what we do not yet know, lit by the red-orange glow of a star that has been trying to tell us something for centuries. We are only now learning how to listen. Betelgeuse is not a crisis. It is a conversation between a dying star and a species just barely old enough to understand what it is looking at. And that conversation is far from over.